Sorry? No. You mean we turn in the tutorials? Yeah. Yeah. Okay, hi class. Okay, let's start our third lecture, okay, which is on another data structure that you're going to learn. Okay, so some admin stuff first. Okay, please submit only one source file for your PSs. Okay, some of you try to write a few Java files and submit. Don't, just everything in one source file. Okay, everything in one source file. Okay, use the template that's given in the write-up. Okay, please use that one. Okay, also don't assume, okay, some of you will say, oh, I just want to tackle the higher subtasks. Okay, if I can solve that, then that means that it should solve for all the rest of the lower subtasks, right? That might not be true, okay? So submit your code. If you have solved the higher subtasks, no problem. Okay, use that same code, submit it for all the lower subtasks also. Okay? See whether you pass all of them. Sometimes it might not be true. You might find, I passed the higher subtasks. Somehow I failed the lower subtasks. That means that somehow there's still some bug in your code. Okay? And also, some students tell me, I keep trying to improve my code, but I still get TLE. I don't understand why I get TLE. My code is as efficient as possible already. Should pass one. So I will tell them, TLE does not necessarily mean that your code is correct. Right? TLE can mean that your code runs into infinite loop or infinite recursion. That's why it's TLE. Yeah. So TLE can also mean that there's a bug in your code. Okay? So it might be efficient, you might have the right idea, but somehow there's a bug somewhere. Okay? So just something for you to think about. Okay. So that's the admin. Okay, so outline for today's lecture. Okay, we'll be doing another abstract data type called the table abstract data type. Okay, so we'll use a problem to motivate it. Basically, it's a census problem. Okay, so we'll try to solve this as usual using 1020 knowledge. Okay, and we'll see there's some performance issue associated with it. Okay, then we'll deal with a new data structure, okay, called the binary search tree, okay, to implement this table abstract data type. Okay. So, before that, let me just go to this web page. Have you seen this web page before? It's the Department of Statistics Singapore. Okay, it contains a lot of statistics on the demographic of Singapore. Okay, so how do they get this? Basically, they conduct census, okay, periodic census of the population. Okay, what's a census? Census is like a survey lah, right? It's like a survey, okay? So in the survey, it's quite complete. They will ask you about lots of stuff, okay? So one of the statistics they have gotten from their census is basically this. Let me go back. Okay, it's called the age-specific marriage rates, okay, of males and females in Singapore. Okay, so here's a graph. After they conducted their census, right, they plotted this graph. Okay, so on the x-axis is basically different age brackets. Okay, and then on the y-axis is the number of people who get married, okay, within that age bracket. Okay. Obviously, when you're 15, 19, at this day and age, nobody gets married, still studying, okay, still playing happily with your friends. Okay. So you'll see that most people get married within the 20-something to 30-something range. Okay, but here you see that there's two curves that are plotted. Okay, one is 2003, one is 2013. Okay, you will see interesting observation here. The phenomenon is that the one for 2013 is shifted to the right, correct? The green one is shifted to the right. Okay, it's same for the males and the females. What does it mean? It means that people are getting married later in life, correct? Yeah, it's shifted to the right. So, after conducting the census, getting these statistics, right, then what's the point? Then the government will come up with lots of campaigns to ask you to get married earlier in life, rather than later. Yeah, so lots of incentive. You get married earlier, you have children at this age maybe, or you get some monetary incentive or something like that. Yeah. Okay. So census is conducting a census is important. Okay. Right. So in fact, in Sun Tzu's Art of War, okay, his first chapter is called the Calculations. Okay, meaning that when you go out to fight a war, right, you have to do all sorts of census calculations. My troop size, the enemy's troop size, the terrain, everything. Okay, all these must be calculated, factored in. Okay, if you do all these things, then he says that you will not be imperiled in 100 battles. Yeah. Okay, so this is the importance. Okay, of gathering all sorts of statistics. Okay, through a census. Okay, in fact, for our course 2010, we have actually conducted almost a yearly census. Okay, except for this year. This year I didn't really conduct a census. Yeah, usually we do it from the Facebook group. Okay, so what do? We basically do a census on the students. In 2010, we gather some particulars about the students. Okay, so the first particular that we gather is basically your age. Okay, age group. So this is last year's data. Okay, 2016 data. Okay, so there are a few age brackets. Okay, 0 to 17, 17 to 18, 18, 19, so on and so forth. Okay, 9 brackets. Okay, so this is what it looks like. Okay, so these are number of people within each of those brackets. Okay, so if you look at it, the mean is about 3.2836. So it's between bracket 3 and bracket 4, which is about right, 21 to 23, right? Since a lot of the males serve the army, so when they come out, they're slightly older than the females. So the age range is about right. Yeah. Okay. Next, we gathered some information on the major that you're studying. Okay. So there are seven different categories. There's computer science, CS, there's business analytics, BZA, computer engineering, CG, CC, comm biology, okay, information systems, science, maths, none of the above. Okay, so this is what we gathered. Yes, I remember the other day someone was posting on Facebook, hey, who is from comm biology? Am I the only unicorn in here? Yeah. So it seems like you're quite correct. Last year was 0, nobody from comm biology. Or at least, if they are there, they didn't participate in my poll. Okay. So, as you can see, majority CS. Yeah, majority CS. Okay. And then, surprisingly, lots from none of the above. So somehow our comm science course is getting very popular among other departments, other faculties in NUS. Okay, I think there are people from arts also. Anyone from arts here? Arts. No one from arts. Okay. Okay, next, nationality. Okay, your nationality. So there's Singaporean, Chinese, Indian, Indonesian, Vietnamese, Malaysian, European, none of the above. Okay? So this is what we have. Okay? So by MOE rules, we should have about 70% Singaporeans lah. Okay, so which is about correct. Here, I have in total participants is 40 plus 13 plus 1 plus 2 is what? 56, right? So 40 of them are Singaporeans. So 40 over 56 is about... Anyone with a calculator? Okay lah, above 70 lah, right? Should be above 70, so that's about correct. Okay? So after that will be the Chinese from China, okay? And Indians from India, and then what's this? 8, none of the above. So from some other place in the world, okay? So I want to ask currently, how many exchange students are there here? Exchange students. 1, 2, okay, 1, 2, 3, 4, 5. Oh, okay, quite a few exchange students around. Okay. I think we're also getting more exchange students every year. Okay. Okay, next is your CAP. Okay, this one we only conducted until 2013 because after that nobody wants to give info anymore. Why? Because, okay, before that it wasn't on Facebook group, it was on some other platform. Right after we shifted to the Facebook group, when you click, people know who you are. Yeah, so after that nobody want to nobody want to take this poll anymore. Okay, so we only have old data, okay, it's 2013 data, old data. Okay, so also a few brackets, okay, tab brackets. So this is what we have. Okay, which, well, I can sort of force a bell curve. Yeah, I'm just forcing the bell curve on it lah. Okay, so exactly bell shape. Okay, but yeah. Okay, so these are some of the information that we gathered, okay, from the census that we conducted. Okay, so what happens after we conduct our census? So we gather our students' particulars. So what do? Okay, we start to do statistical analysis or data mining. Okay. Okay, before we can do that, because we want to use a computer program to do all these things, right? So we need an efficient data structure to store all your student particulars or student record, right? So one abstract data type that you can use to do that is basically the table abstract data type. Okay, so what is a table abstract data type? Yeah, table abstract data type basically is one where you can store very complex objects in the table. Okay, but there is only one attribute, okay, that's important, okay, out of your very complex object. You can have many attributes, but one important attribute, which is called the key. So you use the key to insert this complex object into the table. You use it to search for the objects in the table and to do other data manipulation in the table. Okay, so that's the table abstract data type. Okay, so to deal with, we just deal with one aspect of census as the key. Okay, so we just deal with the age, okay, student age. Okay, so to simplify the lecture, we assume that you are between 0 and 100. Must be true lah, okay? Must be true. Okay, and all integers and all distinct. Okay, so this one might not be very realistic, but okay, assume all distinct age. Okay, so given that we will use the age as the key and we store in the abstract data type table, okay, what are the operations that we want, okay, to perform? Okay, so see, these are some of the required operations. Okay, number one, search whether there is a student with a certain age. Yeah, something we want. Number two, insert a new student, okay, using his or her age. Okay, determine who is the youngest and oldest student. Okay, list down the ages of the students in sorted order. Okay, find a student slightly older than a certain age. Okay, so I give you an age, find a student that is just older than that age. Okay, next, delete an existing student, okay, using his or her age. Number seven, determine the median age of the students. Okay, determine how many students are younger than a certain age. So I give you a certain age, tell me how many students are younger than that age. Okay, so now I have this table, it's an abstract data type. So I will need some concrete data structure to implement it. Right? So what can you use to implement it? So in 1020, you have learned one way to implement a table abstract data type, right? Which is hash table, right? Hash table. That's one way to do it. Okay, so now we will not talk about hash table, but we'll talk about two other different ways of doing it. Okay, number one, very simple, unsorted array. Just use an unsorted array. Okay. So here I have this array, I have 7 ages or 7 items inside. See, all the ages stored here are not in any sorted order. So it's unsorted array. Okay. Now then, how would I implement each of these operations that I want using an unsorted array? First one, age. Search for an age. How would I do it? Or how would you do it? It's unsorted. So just go through the entire array, right? So find whether you can find that particular age or not. So what's the time complexity? If you have n items, it's O(n) time, right? Correct. Insert an age. Or insert is very simple. Unsorted array, I just insert it at the back, right? So this is O(1) time. Find oldest. Same thing, right? So maintain a running maximum. Just go through the entire list, yeah, and then I'll find the maximum age or the oldest one. O(n) time. List sorted age. Well, you have no choice. You want to list sorted age, you have to sort the entire array, correct? So if you use comparison-based sorting, this is O(n) log n. Okay. So find an age older. Find the next age older than this given age. Next older. How do I do that? Okay, this one. How will you do this one? Any ideas? Any ideas? Well, one simple way to do is this. I go through the entire array. I only look at those that are bigger than this age, correct? Because I want the next older one, right? Then I find the one where the difference, where they are different, that age and this age, the difference is the smallest. Okay, among all those bigger than this one. Then that age must be the next one older than this, correct? Yeah? So this one is also O(n) time, right? Go through the entire array, O(n) time. Remove an age. Same thing, it's not sorted, I have to go through the entire thing in order to find the age, right? Remove it, and then maybe you have to close the gap also. So this is O(n) time also, right? Get median. Well, how to get median? Not sorted. So one way, sort it first, right? Sort it, where's the median element? N divided by 2, right? Something like that. Just go to index n divided by 2 or -1 or something like that, right? So can I do it without sorting? You can, right? You have learned something during your Monday and Tuesday tutorials, right? What is that? The quick select or the select algorithm, correct? Select the n or k smallest element inside your array, right? Unsorted array. So in this case, I just select the n divided by 2 smallest element, right? And I can do that in O(n) time, yeah. So O(n) log n or O(n), yeah, using your quick select. Okay. Number younger than age. Again, what you can do, sort it, right? Then use binary search for that particular age, right? Then see where its index is. So total number is basically equals to that index. Younger than it, correct? Or if I don't want to sort it, then what do I do? Just go through the entire array, find everything that is smaller than this age, right? Just keep a count. Right? So this one, if you sort it, O(n) log n. If you don't sort it, O(n) time. Yeah. Okay. So this is what the operations are and their time complexity if you use unsorted array. Yeah. Okay, next. What if you use sorted array instead? So in sorted array, I have to maintain the property that everything must be sorted. Okay, whenever you insert or remove stuff. Okay. So again, if you search for a particular age, what do? Since it's sorted, it's quite easy, right? I can do binary search. Right. So binary search, log n time. Yeah. Insert. Insert, can I just insert at the back? No, right? I have to find the correct spot to insert it. So you have to do something like insertion sort. Start from the back, move to the front, find the place where you need to insert it. Right? So you have to shift things to the right until you find the gap, and then insert it inside. Yeah. Okay. So this one, O(n) time. Find oldest. Very easy. Just go to the back. The last one. Yeah. O(1) time. List sorted ages are also very easy. This one, It's already sorted, so just go through everything, O(n) time. Next order. Next order. So assume that this age given here can be found inside your array, right? So just do binary search first. Find it and then the one next to it, right to its right. That's the next order than it. Okay, so log n time, binary search. Remove age. Also binary search it, right? And then remove it, but you need to close the gap. Right? Close the gap is O(n) time. So this one is O(n) time. Okay, get median. Sorted easy, right? Just go to index n divided by 2, right? Or n divided by 2 minus 1. Number younger than age, same thing. Sort, binary search it, find that age. So its index is basically represents all those that are the total number younger than it. Okay. So log n time. Okay. Okay. So this is what you get if you use unsorted array or sorted array. Okay. So if you try to use hash tables, okay, try to come up with all these how to implement all these operations and the runtime yourself. Okay, this one do it as an exercise. Okay. Okay, so with just 10-20 knowledge, this is what you have. Okay, so I color all those that I deem to be not very fast operations, right? All in red. Right, so you find that unsorted array is probably not as good as sorted array. Yeah. And what I want to point out is basically this. The insert and the remove operations, these are what we call dynamic data structure operations. Why? Because they modify your data structure, right? When you insert stuff or remove stuff, it modifies the data structure. Okay? The rest are just simply query operations. Okay? Query the data that's already present in your data structure. Okay? So, for insert, you see that, well, unsorted array is better than sorted array. Remove, unsorted and sorted are both the same. Okay? So actually it's O(n), if you think about it, still okay lah. Okay? Still okay. O(n) is still quite okay. But if n is large, as I will say, if n is large, then your query will become slow. Okay, so you want to have some data structure where everything here hopefully can be less than O(n). Okay lah, one of it cannot be less than O(n). Which one cannot be less than O(n)? There's no way for you to be less than O(n). Which operation? Definitely cannot be less than O(n). Which one? List sorted ages. There's no way it can be less than O(n), right? Because I need to go through everything. Yeah. Okay, but hopefully I want everything else to be less than O(n). Okay? So just to give a perspective why we always want this O(n) versus O log n. Okay? If n is 8, so log n will be 3, right? Now if I double n, right, then O(n) double also, right? But then log n just increase by 1. Whenever you double n, log n always increase by 1. Okay, so it grows very, very slowly. Okay, so that's why we like log n time operations. Okay? So, can we do better? Of course we can do better, right? Otherwise you don't need to be here. Yeah. Okay, so the way to do better is basically to use what we call a binary search tree. Okay? Or BST for short. So what's a binary search tree? Well, number one, a binary search tree is a binary tree. Okay, so we have already talked about a binary tree during the previous lecture, right? So, for a binary search tree, we need to define certain parameters for each node, okay, in your or each vertex inside your binary search tree. Okay, so we have got the attribute or the parameter left, which represents the left child of x. So for each vertex x, okay, x dot left is the left child of x. Okay, dot right is the right child of x. Dot parent refers to the parent of x. Okay, and dot key refers to the value stored at x. Is the one that we use to insert the object into the binary search tree. Okay, so the way we will implement it is basically unlike your binary heap, okay, which uses a one-base compact array. Here we will use objects and references, okay, to build it. Something like your linked list. Okay, something like your linked list. Okay. So other than this, other than having these attributes and basically being a binary tree, you have a binary search tree property. Okay, what's a binary search tree property? It says that for every vertex, x and y, imagine here I have x. Okay, y, the key of y is smaller than the key of x if y is in the left subtree of x. Okay, so everything here, okay, in the left subtree must be smaller. The key must be smaller than that of x. Okay, and the key of y is bigger or equals to the key of x if y is in the right subtree of x. So everything here in the right subtree must have key bigger or equals to the key of x. Okay. So for simplicity, we just assume all the keys are unique. So we change bigger or equals to just bigger. Okay. Okay. Now the BST property is actually a recursive definition. Okay. So you can look at this example here. It is an example binary search tree. If you look at it, it should, you just eyeball it, okay? It satisfies the BST property, right? Okay, how do we know? I start from the root. Okay, root is what? 15, right? You look at its left subtree. Every vertex here has key value that is smaller than 15, right? And everything in its right subtree has key value bigger than 15. Right? Then I can apply this recursively. In the left subtree, okay, I go to 6. Okay, everything in the left subtree of 6 is smaller than it. Everything in the right subtree of 6 is bigger than it. So we can apply this recursively, okay, throughout the entire BST. Okay. Okay, so what are the operations that we can perform on the BST? Okay, let's now go to Visual Algo. Okay, there are quite a number of operations, so we will look at them each. Okay. Okay, so we start with this particular binary search tree. Can you all see? Make it slightly bigger. Okay. So if you just eyeball it, you can see that this is a perfectly valid binary search tree, right? It satisfies the BST property. Okay. So first thing that we can do, I can search for a value, for a key value inside this binary search tree. Okay, for example, let's say I search for the value 71. Okay, so how do I do that? How do I do that? I will start from the root. Okay, so start from 15. And you check, is 71 smaller or bigger than 15? Okay, if it's smaller, then I just go to the left subtree, recursively search for it in the left subtree. If it is bigger, I will go to the right subtree, recursively search for it in the right subtree. Okay, so 71 is what? Bigger than 15, right? So I will recursively search for it in the right subtree. Okay, then I go to the right subtree, 23, right? 23, is it bigger or smaller than 71? Smaller, right? So I need to search recursively in its right subtree, right? So go to 71. Found it. Okay, so what we can do is that we find it, we just return the value to indicate that we found it. Okay. And for example, how about searching for 7? Again, start from the root, right? So 15. 7 is smaller than 15, right? So search in its left subtree. 6. 6 is smaller than 7, right? So search in its right subtree. Found it. Okay, just return 7. Okay, how about, let's say I search for 22. Okay, start from 15 again, right? Bigger than 15, go to the right subtree or the right child. Smaller than 23, right? So I should go left. But there's nothing left, right? So imagine that actually in the implementation, this one is pointing to null. Okay, the left child is pointing to null. So you find it. I go to the left child, null. Null means that I cannot find it. Okay, I've hit a null pointer, so cannot find it. Okay, so you just return null to indicate that you cannot find it. Yeah. So searching is quite easy, right? For me, searching the binary search tree is quite easy. And do you see that this is actually analogous to binary search in a sorted array? Right? Do you see that? Now let me try again. If let's say I'm searching for 5, okay, searching for 5. I start from 15. 15 is like around the middle of the, if you sort it, it's around the middle, right? Start 15, it's smaller than 15, what do? I recursively search in the left subtree, right? I totally ignore the right subtree, right? It's like sorted array, I start from the middle, smaller, I just go to the left partition. I ignore the right partition, right? So I go left, 6, the middle of that left partition is 6, right? Approximately. And then you can check whether it's smaller or bigger, right? And you just keep going, left, right, until you find it. Right? So here I go left, and then I go right, and I find it. So it's analogous to binary search. Okay? Okay, so this is searching, okay, in your binary search tree. So what other things can you do? Okay, the next one, next two operations are not here, but they are quite simple operations. Okay, let me just go back. Okay, so the other two operations is basically finding the maximum and the minimum element inside your binary search tree. How do you do that? How do you find the minimum? How do you find the minimum? I start from the root again, same thing. Start here, right? Then I just keep searching the left subtree. Keep going left. Then I come here, then keep going left until I hit a node which has got no left child. If that node has got no left child means what? It must be the smallest one inside your tree because I keep going left. Okay? So recursively go left until you hit a node that has no left child. Okay? Or go left as deep as possible. Okay? So this one must be the minimum. Maximum, the opposite, right? Keep going right until you hit a node that has got no right child. So 71 is the maximum. Yeah. Okay, so this finding minimum, finding maximum. Okay, how about the next one? Doing insert. Okay. Next, I must have the ability to insert a new node inside my binary search tree. Okay. So let's look at different cases. Okay, insert one. What do? I need to find the correct spot to insert it, right? Correct. So basically, it's like searching. So I need to search until I find the correct spot to insert it. Okay, let's try. So I start from the root again. Start from 15. 1 is more than 15, right? So it should be inserted into its left subtree. So recursively insert into the left subtree. Okay? So now I'm at 6. It's what? Smaller than 6, right? So recursively insert into its left subtree. So go to 4. 4 is smaller than 4, right? So recursively insert into its left subtree. So at this point, 4's left subtree is null, right? Correct? There's no left subtree. So that's actually the correct place to insert it. Okay? So just insert it as a new left child of 4. Okay? So this insert, let's try another one. Insert 72. Insert 72. Okay, now you tell me. How do you do it? Start from the root again, 15. Then just go right? 72 is bigger than 15, so go right. 23, bigger than 23, go right. 71. I cannot go right anymore, go right is now. So you find that, oh, go right is now, right, means that basically that's where I should insert lah. Okay, so just insert it as the new right child of 71. Okay? Yep. So that's insert. Okay, so the idea behind these operations are quite simple. Okay? Basically, you are performing some kind of search, okay, from the root to find the correct position. Okay? And you'll find that for insertion, a new node is always inserted as a leaf. Okay, because you will hit a left or right child which is null, and then you will insert it as that new left or right child. So it's always inserted as a new leaf, okay, in your BST. Okay, so that's insertion. Okay, so let's look at the analysis. Let's look at the analysis. Okay, search analysis. Okay, what's the runtime for search? What's the runtime for search? For example, I search for 51. I start from 15, right? So I will go from 15, I go 23, then I go 71, then I go left. Oh, found 50. Correct? So I start from the root, I go all the way down to the deepest leaf. Right? So what's the time complexity? Oh, 50. Oh, I'm searching for 51, not 50, sorry. So you go to 51, and then 51, it should be to the right of 51, right? But it's null, so you cannot find it. So you just return null, cannot find it. So actually go from the root, go all the way to the deepest leaf, and cannot find it. So what's the time complexity? OH, right? Where H is basically the height of your binary search tree. Yeah, so OH. So very simple analysis. Find min, find max. Find min, start from 15, go all the way to the left. Find max, go all the way to the right. Yet again, OH, right? Yeah. So this one is OH also. Okay. Next. Insertion. Insertion. How do you do insertion? Yeah, insert 50, for example. Start from 15, go right. 23, smaller, okay, go right. 71. 71 is bigger than 50, so go left. Okay, so insert 50 here, right? 50 inserted properly. Again, you're actually going all the way from the root to some deepest leaf and then adding it as a new leaf. Okay, so this is H, right? OH type. Okay, so you will find that almost all analysis later on you find all OH, lots of OH. Okay. Okay, now let me just look at the code. Okay, so there's a demo code. Okay, there's a demo code for your BST. Okay, so let me just look at the demo code. Okay, so I have two classes here. One is the BST vertex class. One is the BST class. Okay, for the BST vertex, basically I have the few attributes that I need. Number one, I have the parent pointer. I have the left and right child pointer reference. And I have the key. Okay, so height, for now, just ignore it. It will be used in the next lecture. Okay, when I talk about balanced binary search trees. Okay, so this is your very simple BST vertex to represent a vertex in your BST. Okay, next you have your BST class. Okay, so what do you need here? What attribute do you need? You just need one attribute, which is the root. Okay, a reference that points to the root. Okay, the root of this BST. Okay, so next I have the search operations. Okay, there are two overloaded search methods. Okay, so the first one is what the user will call. The user wants to search for a particular value v, right? So you pass in the value v, and then I will call that over the other overloaded search method. Okay, which will start the search from the root. Okay, and then pass in v to be searched for. Okay, so let's look at this overloaded search method. So in this overloaded search method is basically a recursive search method. Okay, so you check if the current node t or current vertex t is null, just return null. That means that I searched all the way, I hit a null pointer, so return null, cannot find it. Okay, else if the key is of t is equal to v, that means that I found it, right? T, the current node, is basically what I want, and just return this node. Okay? Else, if it is smaller than v, just search to the right. Right? Else, it must be bigger than v, search to the left. Okay? So very simple recursive algorithm. Okay? So back to this one, the first search function. So you just return what you find from the search, okay? Assign it to a variable, then you check whether this variable is null or not. Right? So if it's used to null, then you just return -1, saying that you can't find it. Otherwise, you just return the key value. Okay? So this is search. Okay, the rest, you probably can look at it. Okay, let me just go through one more. Find min. Okay, find min. Same thing, I have got two overloaded methods. Okay, so the user will call the first one with no parameters, find min, and then you will call find min starting from the root. Okay, so this is the overloaded one. So just check if t equals to null means that what? T equals to null means actually you don't have a BST. There's nothing. It's empty. So it's empty, I just throw a no such element exception. BST is empty, so no minimum, right? Otherwise, I just check if the left of the current node is null or not. If it is null, that means that, yeah, this node is the minimum, right? So just return the key of that node. Okay, otherwise, just keep going left. Yeah? Yeah? So same thing, find max, okay? Same thing. So we can look at that. Okay, so let me just go back to my binary search tree. Okay, let's do two more operations. Okay, so there is two more operations that I want to talk about before we take a break. Okay, first one is called predecessor. Second one is called successor. So they are sort of mirror of each other. So what I want to do is find the predecessor of a particular value. Find the successor of a particular value inside your BST. So what is predecessor? What's successor? Anyone can tell me? What is predecessor? What is the predecessor of a value? What is the successor of a value? Yeah, what's predecessor? Predecessor is if you have a set of values, right, in the sorted order, right, the predecessor of a value is the one just smaller than it, just before it. Successor is the one just bigger than it, okay, after it, just after it, okay. So let's look at this one, predecessor and successor. Let's say I want to find the predecessor of, let's see, 23. There are actually two cases that we'll deal with. Okay, let's look at the first case. I want to find the predecessor of 23. No, wait. Oh no, I want to find a successor of 23. Sorry. Successor of 23. So what do I do? Okay, before that. First, I need to find 23 first, right? Right? So imagine that, assume that it's already inside. So you will search for 23, you find it. Okay, so 23 is here. So how do you find the successor? In this case, you find that 23 has a right child, right? It has a right subtree. So what is the successor of 23? It's actually the smallest one inside your right subtree, correct? Must be, right? Correct? Because your right subtree contains everything that is bigger than 23. So it's everything that's after it, right? In the sorted order. But I want the one that is just after it, so it must be the minimum one inside your right subtree. Correct? So what I do, I just go to your right subtree and then call find min. Yeah? So find min will just give me 50, right? So 50 is the successor of 23. Okay? So conversely, let's try to find the predecessor. Okay. Predecessor of 15. So how do I find predecessor of 15? Okay, at the beginning, okay, I just go to root, okay, found it, 15 is the root. So what is the predecessor of 15? It is the one just smaller than it, right? So I just go to the left subtree, find the maximum, yes. Because everything in the left subtree are also smaller than 15, right? And the maximum in the left subtree must be the one just smaller than 15. Yeah, so go left to 6 and then call find min. Yeah? Find max, sorry. Find max from 6. It's all the way right. And then you'll give you 7. So 7 is the predecessor of 15. Okay? And now, so this is the first case. First case is when, number one, the value you are trying to find, the successor to, has a right subtree. So it's easy, right? Just go to the right subtree, find the minimum. And the other case is, for your predecessor, okay, you find that the value you want to find the predecessor to has a left subtree. So you just go to the left subtree, find maximum. Okay, so that's the first case. Let's look at the other two cases, the other case. Okay, let's search for successor of, no, predecessor, okay. Let's search for the predecessor of 50. Okay, let's search for predecessor of 50. 50, yeah? So, I searched for 50, I found it. I found 50. I found 50. 50 here. Does it have a left subtree? No left subtree, right? So what do we do? Okay, what we do is this. You start from 50, and then you keep going up. Okay, trace your parent pointers or your parent references. Okay, keep going up. So 50, you will go up to 71, right? Okay, then as you go up, you check. Okay, if I am my parent's right child or not. Okay, so here 50, is it the right child of 71? No, right? It's not. So I assign the current node now to be 71. Then I check, is 71 the right child of its parent? It is, right? It is the right child of 23. So 23 must be the predecessor of 50. Okay, so if you imagine, I start from 50, it's like a car driving up. If I drive up to 71, I do a what? I do a left turn. Okay, it's called left turn. Okay, so you just keep going up from the node until you hit a left turn. Okay? Then the node, your predecessor must be the node. Okay, after the left turn. Okay? So 23 is the predecessor of 50. Okay. Why does this work? Okay, imagine it the other way around. Okay? Now I look at 23. What is the successor of 23? Just now, predecessor of 50 is 23, right? That means that if I look at 23, the successor of 23 must be 50, right? Correct? So 23 here has a right subtree, right? So how do I find the successor? Go down to the right subtree, go left all the way, right? So exactly, right? 50. So from 50, I just reverse the direction. I just go up and then find a left turn. Okay? Correct? That's how you do it. Okay? So, similarly, let's try successor. Okay, for example, okay, successor of 7. I want successor of 7. Okay? Does 7 have a right subtree? Oh, no right subtree, right? So same thing, just go up. So now you keep going until you hit the what? Just now was a left turn. This one is keep going until you hit a right turn, exactly. So you just keep going up until you find that I am the left child of my parent. Okay? So from 7, is 7 left child of his parent? No, I'm the right child. Now assign current node to be 6. Is 6 the left child of his parent? Yes, 6 is the left child of 15. So 15 must be the successor of 7. Okay? And that's how you do it. Okay? Successor, predecessor. Okay, now let's go back to my slide. Okay, analysis, successor, predecessor. So, what is the runtime of successor and predecessor? Same thing, for example, I want to search for the successor of 72. Is there a successor of 72? Right? You look at it, 72 is actually the maximum value, right? So what's going to happen? I start from 72, I'll start going back, right? Going back, and there's no right turn at all. So you will go until you hit the root and then you must stop. Okay, so that's another stopping condition. Right? I hit the root, I don't find a left turn or right turn for my successor or predecessor, I stop. So that means I don't have a successor, I don't have a predecessor. Okay, same thing, if I start from 1, I want to find the predecessor of 1, no predecessor, right? So I just go back all the way, I'll get 15. Okay. So in this case, what is the runtime? Same thing, right? It's OH. So I start from the deepest leaf, go all the way to the root. Okay? So analysis, OH. Okay? Okay, so basically this is your successor, the code for your successor. Okay. So let's look at the overloaded one. Okay. So you start searching from the root. Oh no, you start searching from Okay, first of all, what you do is that you search for the particular value, right? The node of that particular value. Okay. If you can find it, then I will call successor on that node. If I cannot find it, then just return now. I cannot even find the node. Okay. So if I found it, I will call the overloader successor, okay, on the current node that I found. And then I check. If t dot right is not equals to null, that means what? I have got a right subtree, right? So just find minimum in the right subtree. Okay. Otherwise, this is the code for going back up. Yeah. Okay. Same thing for your predecessor. Okay. So you can just look at this code yourself. Yeah. Okay, so we will take a short break for now, and then we'll continue with the rest of the operations, BST, and take a 5 minutes break. Yeah. Sorry? Yes, there is. Yeah, we'll talk about it later. Sorry? Yes, it will be log n if you can maintain a certain property of the binary search tree. Yes. Basically, you have to maintain that the height is log n. The height of your binary search tree is log n. Not necessarily. Not necessarily. So later on I will show you. Yeah. I mean your binary search tree can it can be totally skewed. It can be a degenerate kind of binary search tree. Yeah. If you say log n for a binary search tree, then it is not correct. But if you say log n for balanced binary search tree, it is correct. So we will learn balanced binary search tree next lecture. Hello. Okay, let's restart. Okay, hello. Settle down. Okay. Yeah, I think I am a bit very fast, so I think I will end earlier today. Yeah. Good, right? Yeah, okay. So, okay, we have got two more operations we want to look at. Okay, two more operations. Okay. So the first one is called in-order traversal. What is in-order traversal? In-order traversal is basically one way for you to traverse the entire binary search tree. Okay, so in tutorials you will learn other ways like pre-order, post-order traversal. But here we'll learn in-order traversal. Why? Because you will see that it actually traverses the entire binary search tree in a particular way. Okay, particular way. So what is in-order traversal? Okay, the idea is very simple. Okay, in-order traversal is very simple. What you do is at any node, current node, okay, you will first perform in-order traversal of its entire left subtree. Okay, before coming back to the node, process that node, and then perform in-order traversal of its entire right subtree. Okay, so it's like a three-liner, right? Left, node, right. Yeah. Okay, so let's try to do in-order traversal using this same example. Okay. Of course, I want to traverse the entire subtree. I must start from the root. Okay, so I start from the root. Then I will recursively perform in-order traversal on the left subtree first, right? So I will then go to 6, right? 6, I will recursively traverse its left subtree. So go to 4. 4 recursively traverse its left subtree. Go to 1. 1 recursively traverse its left subtree. You find is now nothing. So that's base case. So you return to 1, process 1, right? Or visit 1. So what we can do is, there are many ways depending on your application, what you want to do when you process it. So for us, let's just print it out. Okay, so print out 1, right? And after that, I will visit its right subtree, right? But no right subtree, right? So I'll come back to 1, finish already, right? So go back to 4, right? So go back to 4, I will process 4, right? So print out 4. Okay? And then after that, visit its right subtree, 5. Right? So 5 don't have a left, come back to 5, print out 5. Okay? Then go is right, no right. Come to 5, finish, go back to 4. So this entire subtree is finished, go back to 6. Right? Print out 6. And then go to right subtree, same thing, don't have a left, go back to 7, print 7, go to right, nothing, go back to 7, then after that, go back to 6, correct. So I'll print 7 here. So 6, finish, go back to 15. So print 15. Okay, now visit is right subtree. Okay, 23 go left, nothing. So go back to 23, print out 23. Okay, and go to his right, 71, go to his left, 50, no left, print out 50. Go right, no right, finish 50, right? Okay, so go back to 71, print out 71. And then after that, go right 72, print out 72, right? And then after that, 72 finish, go back to 71. 71 finish, 23 finish, go back to 15 finish. That's it, right? So you see how the nodes were processed. They are processed basically in what? Ascending order. Yeah, I printed everything out in ascending order. So in-order traversal basically processes everything in ascending order. Okay, so that's very useful for us. Yeah? Okay. So let me just remove all these. Okay, let's go back to my slide. Okay, so what is the runtime of in-order traversal? Okay, so this is a new way of trying to analyze things. Okay, imagine, okay, I have a node. Okay, of course I have a parent coming here, I have a left and right child, right? So I have a left subtree, I have a right subtree, and this is my parent. Okay, so I'm looking at this node. How many times during in-order traversal is this particular node visited, so-called? Number one, the first time, when from my parent I recursively call in-order traversal, right? So I'll visit this once, right? Then after that, I will recursively visit the left subtree, right? So once this is finished, I will come back. So this is second time I visit, right? So second time, right? Then after that, I recursively visit the right subtree, right? Then I come back, third time, right? After that, I'll finish the recursive call to this entire tree, right? So I'll move up. After that, will I ever come back to this node again? No, right? So for any node in your BST during in-order traversal, I only maximum visit it 3 times. So what's the runtime of in-order traversal? Yeah, it's just 3n, right? Which is equals to big O of n. Okay? Right. This is your in-order traversal analysis. Okay, this is what I said. Okay? Next, the last one, which is the most complicated operation, okay, is the removal. Okay, to remove a particular value or key from your BST. Okay, so there are a few cases. Also, there are 3 cases. Okay, let's try all of them. Okay, for example, I want to remove the node or the vertex with value 5. Value 5. So what do? First, I need to search for it, correct? I need to search for it, right? Assume that I found it. Okay, I go 15, 6, 6, go 4, 4, go 5. I found it, right? Right. So I found it. How do I remove it? Well, you'll find that 5 here is basically a leaf, right? So removing it is quite easy. Just remove that. Right? Just remove it. Yeah. Set the right child of 4 to now, and then I remove 5. Right? That's it. Very easy. So this is the first case. When the node you want to remove is a leaf. Right? Next case. If let's say I want to remove 23. So search for 23, right? 15, go right. 23, oh, found it. Okay, in this case, 23 is not a leaf. It is an internal node. It has got a right child. So can I just remove it? What happens if I just remove it? If I just remove it, I disconnect the entire tree, right? Yeah. So what I do? What I do is this. I take my only child, right? I connect it to my parent. Okay, so set the parent of 71 to be 15, right? And then set the right child of 15 to be 71. So connect your parent to your right child. Okay? Then in that case, you bypass 23. Right? Okay? So no problem. Okay? If you have just one child, whether it's a right child or it's a left child, all you do is connect your child to your parent and connect your parent to your child. Then I will bypass you. Yeah? And do I violate BST property? No, right? If my parent is bigger than me, then it must be bigger than anything in my right subtree or left subtree. Doesn't matter, right? So you can still connect. If my parent is smaller than me, then same thing, right? You can connect to any child of your left or right subtree because they are all bigger than your parent. Yeah. Okay. So this is the second case when the node you want to remove has only one child. Okay. Next, I want to remove 15. Okay. I want to remove 15. Okay. 15 has got 2 children. Oh, what to do? I cannot remove it. Also, I don't have a parent anyway. 15, I can't connect. Even if I have a parent, let's say 15 has got a parent. How do I connect to which child? You cannot connect to both child, right? To both children, because your parent might already have another child already, right? Then I connect both child, then it's not a binary tree anymore. It becomes there's a node with 3 children. Don't work. Okay, so don't work. So what do you do? So what you do is this. Okay, from 15, find your successor. It has 2 children. It must have a successor, right? Right. So find your successor, which is what? Let's go right and then find minimum, right? Which is 50 in this case, right? Take 50 and use it to replace the value at the node. So take 50, replace 15. Okay? Then after that, remove your successor. Delete your successor. So when you replace 50, okay, take 50, I replace this, so this becomes 50. Number one, you see that 15 disappeared already, right? So called I remove it because I replaced it with 50. But then now I have a duplicate, right? I have 250, right? So I need to remove this 50. Okay? So what you have will be like this. Go down, find my successor 50. Ding! Okay. Sometimes this animation is very hard to trace, but you understand what it's doing, right? Ding. Yeah. Okay? 50, replace 15, delete that extra 50. Okay? So this is what you have. Okay? Okay, so basically 3 cases. Deletion of a leaf, deletion of internal node with 1 child, deletion of internal node of the root with 2 children. Okay, so 3 cases. Okay, now let's do analysis on that. Okay, removal. Okay, number 1, why do I use the successor? Okay, why do I take the successor, replace the value, and then delete the successor? Number 1, if I take my successor and replace my value with my successor, number 1, it does not violate BST property, correct? Yes? I take the smallest one in my right subtree, right? Replace me. Then the smallest one must still be smaller than everything else in the right subtree, right? So that's still valid. Number 2, my successor must have only at most 1 child. Correct or not? Why? Successor is the smallest one in the right subtree, right? Smallest one means what? It definitely cannot have a left child. If it has a left child, means that it's not the smallest one. Correct? So at most it has a right child. Or it might not have either children, so it's a leaf. Right? So now deleting. So I replace, right? Now I need to delete my successor, right? So now deleting my successor is simple, right? Because it's either deleting a leaf or it's deleting a node with just one children. Yeah, so it's simple. Okay? So that's why you want to find the successor. Replace it with the successor. Okay? Now question, can I use predecessor instead? Can I use predecessor instead? Is it the same? Does it still work? Yeah, I can, right? I mean, I have got two children. That means I must have a successor. I must have a predecessor, right? So replacing myself with my predecessor does not violate BST property. Same idea as replacing it with successor. And then predecessor must be the biggest one in its left subtree, so it cannot have a right child. So it only has at most one child. Okay? So it's the same idea. I can also use predecessor. But here we just choose to use successor lah. Okay? Okay, so this is basically what I've said. Ding. Okay, let's analyze the runtime then of deletion. Okay, or removal. Okay, number one, in order to delete a particular vertex, first I have to find it, right? I have to search for it. I will find it in OH time at most. And then there are three cases, right? V has got no children. No children, just very easy. Just bypass it, so O1 time. Yeah. Next, it has one child, either left or right child, right? Just point my parent to this child and point my child to that parent, so O1 time also. Has two children. So number one, find the successor. Okay, find my successor, so OH time, right? Then replace my key with my successor's key, O1 time, and then delete my successor, OH time again. So you see that for these three cases, none of them is more than OH, right? That means that for deletion, it's also OH time. Okay, it's also OH time. Okay, now let's go back to the code. Okay, just now I did not show you insert and removal because these are the two which are basically, like I said, these are dynamic data structure operations. You are changing your data structure. So when you change your data structure, what happens? You need to set all your references, all your pointers correctly, right? Yeah, so here I will just sort of give you an idea how we do it. Okay, let's go back to insert. Let's go back to insert. Where's my insert? Where's my insert? Ah, insert is here. Okay, so insert, same thing. I have got two overloaded methods. Okay, the first one, insert a particular value. Okay, the user will call this insert a particular value into BST. Then in its implementation, it simply calls the overloaded one where you start inserting from the root. Okay, so T will be the current node, P is the value you want to insert. Okay, so for insert, you will check if T equals to null, that's the point where you want to insert it, right? I search all the way, or I come to a point where it's null. So I will just create my new BST vertex with value V and then return it. Okay, otherwise, there are two options. Number one, the current key is smaller than V, so I will recursively insert it to the right. Okay, recursively insert it to the right, or I recursively insert it to the left. Right? But look at how we manipulate the pointers here. Okay, we take what is returned from the insert, right? And then point T dot right to it if the current key is smaller than V. Okay, and also set T dot right dot parent to point to T. Okay, so for the other one is set T dot left to point towards return, set T dot left dot parent to T. Okay, let me just show you an example. For example, if I have this, just draw it up. (20, 18, 22). It is 20. Okay, for example, I want to insert 19. So I'll start from the root, right, which is 15, right? So from root, okay, currently T will point here, correct? So 19 is bigger than 15, right? So I'll recursively insert into the right subtree. Then T will be here, right? Yes? And then I'll recursively insert into the left subtree because it's smaller than 15. And T will be here, right? After that, I'll recursively insert into the right subtree of 18. Right subtree is now, right? Which is correct. So I will create a new node 19. Okay, and then return this new node. Right? Yes, when I return it, okay, which one do I go back to? This one or this one? This one, right? So t is here, correct? In the previous call. So t dot right will point to what is returned. Correct? And then t dot right refers to 19, right? Dot parent will point to t. So this one parent point to here. So I established this link. But that's not the end, right? My recursion will keep rewinding all the way back to the root, right? So what happens? I am just re-establishing all these links. If you think about it, right? That's it. Okay? So this is how we manipulate the references to make sure that it's correct. Yeah? So this is insert. Okay. Now let's look at deletion. Deletion is slightly more complex. Okay, same thing. If I want to delete a value, I call the first method. So delete v, which we'll call the overloader method, where you start deleting from the root. Okay. So this is the overloader method. Okay. So when t goes to null means that I try to search for v, I cannot find v, right? So I just return null. Return t, cannot find. Okay. Otherwise, there are a few cases. If t is smaller than, the key of t is smaller than v, that means I will recursively delete v from the right subtree. Right. Okay, so this is this. And then if it is bigger than v, I'll recursively delete it from the left subtree. Okay. So here you see, whatever is written, I'll set t dot right to it. This one, whatever is written, I'll set t dot left to it. It's basically what is being done in the insert, right? It's the same idea. Okay. Else means I found it, right? I found the node that I want to delete. Okay. Now there are three cases, right? Like I said, either it's a leaf, or it's an internal node with one child, or it's some internal node or root with two children. Okay. So this is the first one where it's a leaf. Okay. If it's a leaf, I will just return null. Okay. T set to null, return t. Okay. At the end here, I always return t. Okay. Otherwise, it must be a case where I have got only one child. Okay. The second case lah. So there are two sub cases here. One is when I have a left child. Oh no, I don't have a left child, but I have a right child. Right. Then I'll just set t dot right dot parent, point to t dot parent, and then t point to t dot right, and then return it. Okay. Otherwise, it's the other one. So it's t dot left dot parent set to t dot parent. T is assigned t dot left. Okay, let's again use back my same example. 15, 7, 20, 18. Okay, now I insert 19, right? Okay, 22. For example, let's say I delete 7. Delete 7. So I will start from 15, right? So t will point here, right? Like recursively delete left subtree. So t will point here, right? 7. Oh, I found 7. So it must be the first case, right? This one, right? Right. So here I set t to be null. Instead of pointing this set to null, right? Then I return t. So t will be returned to the previous caller, right? So the previous caller is what? This one, right? Right. So t dot left will be assigned to what? Null. Correct? Because I said I return null to it. Okay, so this one is gone, and then this one will basically be null. Right. So I bypass my leaf. Okay? Can? Okay, so this is deleting a leaf. Okay. How about deleting 18? So same thing, right? Start from 15. T point 15. Then I'll recursively delete right subtree, right? Then I recursively delete left subtree, right? So 18 is here, found it. So which case is it? It's the case where you have got one child, right? So which one? Which child? I have a right child. Okay, so it's this one. Is this case, right? So here I'll say t dot right dot parent. So this 19, right? Dot parent will assign to t dot parent. T dot parent is 20, right? So this one assigned here. And then t is assigned t dot right. So now t is assigned this one. Then I return t. right? So I return 19 to my previous caller, right? So in the previous caller, this is pointing to 20, right? So which one is it? The previous caller is which one? The previous caller is, yes, this one, same thing, is this one, right? So t dot left, so this t dot left will be assigned to 19, right? So I set parent to point to this one. So this one is bypass, 18 is bypass, okay? So basically here I have set the link. I bypass 18. Okay. Then that's not the end. I will keep going backwards, right? But it's the same thing with the insertion one. You just reset. You are just repointing all your pointers all the way back to the root. Okay. Then, so that's the other case where you delete a node with 2 children. Okay. This one you try and trace it yourself. Not that hard lah. So once you try and trace it, it's not that hard. Okay. Okay. So basically, this is what I want to show you here. Okay, then I have this BST demo class. You can run it and then you can sort of see how it all works. Okay, so let me go back to my slide. Okay, yes. Let me go and just tell you about 2 more operations. Okay, where is it? Okay, these I won't talk about that much today, because these operations, I will talk about it next lecture. Okay, but just introduce it. Okay, these 2 operations are not yet inside VisualGo. Okay, so this is called the select and rank operation. Okay, select and rank operation. So what is select operation? Select is like a quick select, and the idea. So select k means select the value v of the kth smallest element. Okay, you return, select k returns the value v of the kth smallest element. Okay, in your BST. Okay, so imagine I have a BST like this, right? Right. So if you do in order traversal, you find that basically all these nodes are ordered in this way, right? 4 will be the first smallest element, 5 will be the second smallest element, so on and so forth, right? Okay, so let's say I want to return value of the 5th smallest element. Which one will be returned? What is the 5th smallest element here? 15, right? So select 5 will return 15. Okay, so the opposite is basically called the rank. Okay, I want to find the rank of an element with the value v. Okay, rank means that give me its position inside the ordering lah. Okay, so it will return the rank k. Okay, so what I mean is this: a value v. Okay, a particular element, if it is the k smallest element, right, then you can say that k is the rank of that element. Okay, k is the rank of that element. So when I want to find the rank of a particular value, I will search for that value and then return its rank. Okay, so for example, let's say I want to find the rank of 4. Rank of 4. So I'll find 4, right? 4 is here, right? So what's its rank? Its rank is 1. So return 1 because it's the smallest element. Okay, rank of 6. 6 is here, 3. So I'll return 3. And so on. Yeah. So these 2 operations, select and rank. Again, I will talk about it in more detail in the next lecture. Okay. Okay. So I've already shown you the BST demo program. Okay, so you know that after doing PS1, free code will not go very far. So you can use this demo for your PS2 purposes. Okay, but you need to know how to modify it lah. Okay, so now back to our table implementation. Yeah. So we have an assorted array. We have a sorted array implementation. Now we can have a BST implementation. Okay, BST implementation. So how would I implement search for an age if I use BST? So just use the search function, right? Search operation, right? So this is OH type. Insert, just use the insert operation, OH type. Find oldest, just call find max, right? Find max, OH type. List sorted ages, how do I do that? Perform what? In order traversal, right? perform in-order traversal, I will list everything in sorted order. So it's O(n) time. Next order, what do I do? How do I find next order? Successor, right? Use successor. Yeah, successor of this particular age. Yeah. So this is OH time also. Remove an age, just call the remove or delete operation, OH time. Okay, so you have 2 more get medium, num younger. Okay, this one we reserve it for next week. Okay. So, as you can see, for BST, almost everything is OH time, okay, except for least sorted age, which must be ON time. Okay, so it depends on what is H, right? Now, I can have such a tree. Can I? I can, right? This is a degenerate tree. It's totally skewed to the right. Yeah, how do I get this tree? Well, I can first insert 4, right? Then I insert 5, then I insert 6, insert 7, 15, 23, 50, 71. In that order, then I get this totally skewed tree, which looks more like a linked list, right? So what is the height of this tree? Yeah, it's ON. So since every operation, almost every operation here for BST depends on H, right? Then now H is actually N, so everything here becomes ON. Then my BST is actually quite useless, right? So this particular lecture, what was this? The point of this particular lecture? The point of this particular lecture is to allow you to understand what's the BST, and next lecture will tell you how to balance your binary search tree. Okay, so that the height is always maintained at big O of log n. Okay, in that case, all your operations will be big O of log n. Okay. Oh yeah, can you spot another worst case scenario? Insert the opposite way, lah, right? First 71, then 50, 23, then everything is skewed to the left. Yeah. Okay. Okay, of course we can do better. Next lecture. Okay, so basically that's it for this lecture. Continue your training, okay, on BST. Okay, so that's it.
I said I will be trying to implement the hash map.
Uh-huh.
Make a lot of compile error. If tomorrow you bring also wrong. So today I just download and see MPL. So I need to do my master.
Tomorrow afternoon, same thing.
After 5 or
After 5.